In this lesson, we're going to introduce the idea of the determinant of a matrix, talk about how to find it for various size matrices, and then in later lessons, we'll talk about how it can be useful and what it can tell us about that matrix. So first off, if we have a 2 by 2 matrix, the determinant of this matrix, we have a couple different notations. So first of all, det A, that's one way of doing it. This looks like the absolute value of A. It's not, it's the determinant, but that's what it looks like. Please notice that when we write a matrix, we've been writing with these little square brackets. Notice if you ever see the matrix inside of these straight lines, basically like an absolute value again, that is a direction that you're supposed to be taking the determinant of that matrix. So anytime you see just the straight lines, that is, it's not, oh, here's a matrix. It's hey, do something to this matrix. Kind of like if you ever see, just the number 16, fine, oh, okay, it's number 16. But if you ever see, something around it, like the square root, that's an indication to do something to that 16. In this case, take the square root of that number. So anyway, so these are all the different ways of denoting the determinant, but please notice to actually calculate the value of the determinant, we're going to multiply the main diagonal, A times D, minus multiply the other diagonal, B times C. That's it. And we can only find the determinant of a square matrix. So one more time, this calculation, AD minus BC, we saw that in the last lesson. Just a reminder, in the last lesson, we used that determinant on the bottom of a fraction. Here, I don't want the fraction. I want just whatever number you get. Okay, so don't put it 1 over like we did before. So to practice this a little bit, let's find this determinant. Again, please notice the straight lines around the matrix tells us that we're going to do something with this matrix. We're going to find this determinant. So multiply the main diagonal, 2 times 2, minus multiply the other diagonal, 1 times negative 3. And so the determinant is 7. And we're not really getting into what that means or anything like that. We're just, right now, it's just something we're doing to matrices. We will get into why we would want to find the determinant as we go along here. Let's look at this example, find this determinant. Okay, one more time, multiply the main diagonal, 2 times 2, minus multiply the other diagonal, 4 times 1, and this time we're getting an answer of 0. Okay, that's interesting. Determinants can be positive or negative. They can be fractions as long as the entries are fractions. They could be 0, right? We have an example here where the determinant is 0. So it really could be any number. Now, this is the determinant of a 2 by 2 matrix. Cool. To find the determinant of larger matrices, we first need to talk about what are called cofactors and minors. So to find the determinant of find the determinant of a larger matrix, we were going to use minors and cofactors. Okay, so let me explain what I mean by these. The minor of entry Aij, which I'm going to write Mij, is the determinant of the matrix found by removing row I and removing column J of matrix A. I'm going to show you what I mean by this in just a minute. It sounds a little weird, but it's going to be fine. But this is what we mean by minor. A minor is basically a smaller matrix that we find the determinant of. And then the cofactor of entry Ij, which I'm writing Cij, is basically take that minor that we calculated and multiply it by -1 raised to the power. Now, please notice, -1 to a power is either a -1 or a +1. And so the only thing that this will possibly change is the sign of the minor. So either the minor will be the cofactor if -1 is raised to an even power, or the minor will be the opposite of the cofactor if -1 is raised to an odd power. And then what is this power that is being raised to? Well, I plus j power. So take the row number plus the column number, and that's the power that we raise it to. Okay, before we use this to calculate determinant, let's just take a minute to just play around with these minors and cofactors, because I've said a lot of words. Let's see some numbers. Let's just find some minors and cofactors. Just to be completely clear, this example is just practice. It's just, let's mess around a little bit. This is not how a homework question would be written. It wouldn't say, find some minors and cofactors. No. This is just our chance to play around with it a little bit to make sure we understand what we mean by minors and cofactors. After this slide, then we're going to get into, okay, now what is our process going to be? How do we use these minors and cofactors? Right now, let's just play around with it a little bit, just messing around finding minors and cofactors. So let's start, and we're just messing around. I'm just going to pick a number at random. I'm going to pick this 3, just at random here. So please notice that that entry, which by the way, we call that A, the entry is A, is little a, and that's in row 2, column 1. So that'll be A sub 2, 1, and that's a 3. Okay. And that is not the minor or the cofactor, that's just the entry. The minor, M21, is going to be the determinant of the smaller matrix, where row 2 is removed from the matrix and column 1 is removed from the matrix. So we take out the row containing the 3, could take out the column containing the 3. And notice that what we have left is a smaller matrix where the top row is 2, 1, and the bottom row is 0, 1. And the nice thing about this minor is it is the determinant of a 2 by 2 matrix, which means we now calculate this determinant like we did the last couple examples. So I'm going to multiply the main diagonal minus multiplying the other diagonal, and I get an answer of 2. So entry 2, 1 is 3, minor 2, 1 is 2, and then the cofactor 2, 1 is going to be, so again, it's negative 1 raised to the 2 plus 1 power times the minor, and we just calculated that minor as a 2. So once again, please notice this is negative 1 raised to a power, which is either going to be a positive 1 if it's raised to an even power, or negative 1 if it's raised to an odd power. In this case, it's negative 1 raised to an odd power. It's raised to the third power, which means that my cofactor is going to be negative 1 times 2, or negative 2. So notice that the minor is the opposite of the cofactor. If that negative 1 was raised to an even power, then the minor would be the same as the cofactor. They would be equal to each other. Okay, so that's an example of finding a minor and a cofactor. Let's do another one just to make sure we got it. Once again, I'm going to pick an entry completely at random. How about this time we do the, how about this 1 right here? Totally random. I'm just picking whatever. So first of all, notice that that is the entry in row 1 and column 3. So A13 is equal to 1. M13, so again, we're going to find the determinant. We're going to remove the row containing that entry, remove the column, and then we find the determinant of the smaller matrix. So multiply the main diagonal minus multiplying the other diagonal. And so my minor in this case is 4. Okay. C sub 1, 3 is equal to negative 1 to the 1 plus 3 power times the minor we just calculated, which is 4. Notice that in this example, the negative 1 is raised to the 4th power, so it's an even power, so which means negative 1 to the 4th power is positive 1. So 1 times 4 is 4. So in this example, the cofactor was the same as the minor. In the previous example, the minor was the opposite of the cofactor. Okay, so we're going to do more of these. We're going to use these to calculate determinants, but this is just the idea of what does it mean to be a minor? What does it mean to be a cofactor? All right, so let's now talk about how these can be used to calculate determinant. So the determinant of a square matrix, by the way, you can't find the determinant of a non-square matrix. But to find the determinant of a square matrix, it's the sum of the entries of each row or column. Sorry, let me try it again. It's the sum of the entries of any row or column multiplied by the corresponding cofactors. In other words, I'm going to pick a row or a column. I'm going to take each of the entries of that row or column, multiply those entries by the cofactors, and then add the results. So let me show you what this looks like. And we'll do a couple of examples here. Once more, I can pick any row I want. I can pick any column I want. Does not matter. I want to show you guys a couple of different ways I've seen students organize their work for these. So first of all, the determinant of A. Once more, I'm going to pick any row. I'm going to pick any column. So how about I'm going to pick the first row just because I'm not feeling really creative right now. Um, so I'm going to take each of the entries of that. You know what? I take it back. I'm going to rearrange this. Whoops. I'm going to arrange this just a little bit. I'm still going to pick the first row or column, but I'm going to arrange this just a little differently. So as I said, there's a couple of different ways that I've seen students organize their work. One option is to create a little table here. So the first column is going to have all the entries of that row that I picked. So the entries are 0, 2, and 1. Okay, so the A's are the entries. This, I should have given myself more space. Hold on, let's try it again. Okay, 0, 2, and 1. Okay, the next column is going to be the minors. So each of these minors, for each of these entries, I'm going to find the smaller matrix where we remove the row for that entry and the column for that entry. So for example, the 0, if I remove its row and I remove its column, we're left with a smaller matrix, -1, 2, 0, 1. And if I find that determinant, multiply the main diagonal minus the other multiplying the other diagonal, and I get a minor of -1. Okay. My third column is going to be the cofactors. So again, the cofactor, we're going to take -1. Now please notice that that 0, that entry of 0 is in row 1 and column 1. And then we're going to multiply it by the minor that we just calculated, which was -1. -1 squared is positive, so I'm getting a -1 for my cofactor. And then the last column asks me to take the entry and multiply by its cofactor. So this is what I said on the previous slide. We're going to take an entry and multiply by its cofactor. So in this case, it's going to be 0 times -1, which is 0. Let's do that again for the other entries here. So let's move on to the 2. Let me erase here a little bit. Let's move on to the 2. If I remove its row and its column, I'm left with a smaller matrix where the entries are 3, 2, 4, 1. Multiply the main diagonal minus multiply the other diagonal, and I get -5. For the cofactor, that 2 is in row 1, column 2, and we're going to multiply by the minor, which is -5. So -1 cubed is -1, and then -1 times -5 is 5. Okay, so my cofactor here is +5. And then I'm going to take the entry, which was 2, and multiply by the cofactor, which is 5. And I get an answer here of 10. Finally, for that 1, let me one more time erase this. If I remove the row and column containing that 1, I'm left with the smaller matrix, 3, -1, 4, 0. Multiply the main diagonal minus multiplying the other diagonal. I'm getting an answer of 4. I just realized this is the same matrix from the last example. That's hilarious. Anyway, doesn't matter. So we found that my minor is 4, -1. So that entry, that 1, is in row 1, column 3, times my minor. And -1 to the 4th times 4 is just +4. Okay, in the last column, I'm going to take the entry, which was 1, multiply by its cofactor 4, and I get an answer of 4. Okay, and now to find the determinant, I'm just going to add this last column. So I'm finding that, let me get that out of the way. I'm finding that the determinant of A is equal to 0 plus 10 plus 4, which is 14. So the determinant of this matrix is 14. Okay, so this is one way to organize your work. And if you like it, great, go for it. But basically it's do all the minors and cofactors and separately, multiply the entries and the cofactor separately, and then add the results. We're going to do another example with a different method where it kind of all is done at the same time. But I want to point out something interesting here. Did any of this work even matter? Because when I do A times C, if A is 0, who cares what C is? Multiply by A and you're going to get 0 anyway. So it's kind of nice to observe that we could save ourselves some work here by picking rows or columns that have the most zeros. Because if an entry is 0, when we multiply by the cofactor, it's still going to be 0. So why bother finding that cofactor to begin with? So let's consider this example. In this example, there's 2 zeros. So I can pick any row I want. I can pick any column I want. But I'm going to pick one that has the most zeros. In this case, I'm going to pick the third column. And again, it doesn't matter. First or third columns are great. Second or third row are fine. No matter what, you're going to have 1 0, which is great. It'll save you some effort. Yeah, you have some choices here. Now, as I said, for this method, I'm going to do it all at once. The determinant of A is equal to. So I'm going to take the entries of that column. So that was the 3, the 0, and the 4. Now, for that 3, we're going to multiply by the cofactor. So the cofactor would be -1 raised to the 1 plus 3 power, because that 3 is in row 1, column 3. So raised to the 1 plus 3 power. If I remove the first row and the third column, I'm left with a smaller matrix, 1, -1, 0, 1 plus. Okay, so the point here is I'm kind of doing everything at once, right? This is my minor, this is my cofactor, and this is multiplying the cofactor times the entry. I'm just doing it all in one shot. If you don't like this method, fine, don't sweat it. That it's not a big deal. It's okay. The next entry is a 0. In other words, who cares what it's multiplied by? It doesn't matter. It's getting multiplied by 0. I'm going to skip that altogether because who cares? And then I'm left with the 4. So the 4 is going to be times -1 raised to the 3 plus 3 power, because that's in row 3, column 3. If I remove row 3 and column 3, I'm left with -2, 2, 1, -1. Okay, and now what I've left is to evaluate these two determinants and come up with an answer here. So I've got 3, -1 to the 4th power is 1, so that doesn't matter. And then multiply the main diagonal minus the other diagonal. The 0, who cares? 4 is multiplied by -1 to the 6th, which is +1. And then that last matrix, multiply the main diagonal, which would be 2, minus multiply the other diagonal, which is also 2. I got another 0. That's cool. So my final answer is just 3. So it's nice that this turned into a 0, but I mean, it doesn't matter. There really wasn't much work there to do, and we still got an answer. So this is, again, this is a second way to organize your work. Use whatever method you like best. It doesn't matter. Okay, so these are 3x3 matrices. That's great. Oh, they're cute 3x3 matrices. But what if we had a bigger matrix? What if we had a 4x4 matrix? Okay, like this. Oh, no, we're jumping right ahead to a 5x5 matrix. Cool. Okay. If we have to do a 5x5 matrix. Okay, first of all, I'm going to show you the dumb way to do this, but that's okay. Okay, let's talk about the dumb way to do it. The dumb way would be to pick a row or column like the second row. Notice that to find the determinant of a 5x5 matrix, by the way, I'm going to erase all this. You're not going to want to write this down, but to find the determinant of a 5x5 matrix, I'm going to pick that row, and it's going to be -1 times -1 to the 2 plus 1 power, because that's in row 2, column 1, times the smaller matrix, where we remove its row, remove its column, and we're left with a 4x4 matrix. 2, 0, 3, -2, 4, 0, 2, 3, -2, 0, 2, 1. Okay. To find the determinant of this 5x5 matrix, I broke it down into a 4x4 matrix, except when I also have 1 times -1 to the power times another 4x4 plus 3 times -1 to a power times another 4x4. To find the determinant of a 5x5 matrix, I will break it down into 5 4x4 matrices. And then this matrix, I have to break down into 4 3x3 matrices. It's a lot of work. So let me start by showing you that if if there's a lot of zeros, use the zeros, please. Just make your life easier, not harder. For example, in this case, certainly I want to pick the top row. Now, obviously, if we had a 5x5 determinant or a 5x5 matrix, which is a random matrix, obviously it's not going to have a ton of zeros like this. And so in later lessons, actually in the next lesson, we will talk about what if there is not a lot of zeros. Are there any options available to us? In fact, we'll broach upon that a little bit before we're done today. But as long as we get all the zeros, let's just use it. So notice that if I were to take that top row and focus on it, the determinant of A, I can just ignore all those zeros, and I've just got that 4. Now it's going to be 4 times -1 raised to the, well, let's see, that's in row 1 and column 5, times the smaller matrix. So let's remove its row, let's remove its column, and we're left with the matrix, let's see, -1, 1, 3, 2, 0, 2, 0, 3, 3, 4, 0, 2. Hold on. Yeah, that's okay. Okay, yeah, we're fine. We're fine. Fine. Okay. And then 1, -2, 0, 2. Okay. So fine, great. This is nice, but once again, we're left with a 4x4 matrix. Okay. First of all, the numbers out in front become 4 times, yeah, 4 times 1 is just 4. Okay. So that's great. We're left with a 4x4 matrix, but again, 4x4 is still a lot of work. Let's again that's a hard word. Let's again strategically pick a row or column that has a bunch of zeros. And in this case, let's pick this column. So we've already got the 4 out in front. Now we've got 3 times. So 3 is going to be -1. So this time that 3 is in row 1, column 3. And then if we remove its row and its column, I'm left with the smaller matrix 0, 2, 3, 3, 4, 2, 1, -2, 2. Okay, cool. And so now, again, all those zeros definitely paid off because now I'm left with a matrix, a 3x3 matrix, and we know how to calculate this determinant. So first of all, out in front, once again, we have a +1 here. So we're going to have a 12. And now we're going to multiply by the determinant of the 3x3 matrix. Pick any row or column, doesn't matter. I'll just pick the top row because it's got the 0. So, who cares what the 0 multiplies by? Plus 2 times -1 to the 1 plus 2 power because it's in row 1, column 2, times the smaller matrix where we remove the row and the column. 3, 2, 1, 2. Plus 3 times -1 to the 1 plus 3 power. Smaller matrix, if we remove row 1 and column 3, would be 3, 4, 1, -2. So 12 is multiplied by, let's see, -2 times 6 minus 2, plus 3 times -6 minus 4. So we have 12 times, let's see, -2 times 4 is -8. Minus 3 times -10 is -30, or I guess plus -30. It's fine. So 12 times -38, which is, oh, I'm in trouble here. Hold on. For 400, or first of all, negative, let's see. 452. No, that's not right. Hold on. Let's try this one more time. This is funny. I'm making a video and I'm trying to do this in my head. It's ridiculous. It's definitely 400, negative 400, and 56. Pretty sure that's the right answer. You know what? I'm just going to assume it's the right answer. And if it's wrong, oh well. It's a mistake in the videos. I'm sure it's not the first and it won't be the last. Anyway, the point is we've got an answer here. All right. Well, as I mentioned earlier, we are going to a little bit now and certainly in the next section be looking for shortcuts, ways to find determinant without actually doing all the work. And so to get us there, let's consider this example. Let's find this determinant. And to do it, I'm going to focus on this column. So I'm going to take, so the determinant of A is equal to, so let's see, it's going to be 5 times negative 1 to the 1 plus 1 power times the smaller determinant, which is 1302. And of course, the nice thing about picking that column is all the zeros, right? The only thing that matters is that 5. And so now if I do this computation here, we get 5 times 1. And then I'm going to write this a little differently to emphasize something here. Notice to find this next part here, I'm going to multiply the main diagonal. So it's going to be 1 times 2 minus the other diagonal. But of course, that's just going to be 0. And so I get an answer of 10. But the important thing that we want to note from this is that my answer was the product of these 3 entries. So notice that the determinant of a triangular matrix is the product of the entries on the main diagonal. So that's really useful. Notice, by the way, another word for a triangular matrix is a matrix in echelon form. So notice that if the matrix is in echelon form, our determinant is just the product of the entries on that diagonal. That's really useful. Now, of course, what we haven't talked about yet is if I gave you a different matrix, not this one, but what if I gave you a different matrix? If I were to take that matrix and use row operations to put it into echelon form, will I be changing the determinant or will it stay the same? Because that seems like it's a nice little shortcut using row operations to take a determinant which is kind of messy. And by the way, 3 by 3 is fine, but what if it was a 5 by 5 matrix? If we can, that's going to be a giant mess to try to find the determinant. But if I can use row operations to put that 5 by 5 into echelon form, well, now all I need to do is multiply the diagonals and I'm done. But what we haven't considered is, as I do that process, as I put it into echelon form, am I changing the determinant? And we're not going to answer that question right now. That's going to be a question that we are going to be considering in the next lesson. But for right now, that is the end of this lesson. Thank you very much for watching.